Okay, so we're going to talk about Fourier series and Fourier transforms. Fourier series are the series we've already talked about, where it's just a sum over sinusoids with increasing integers as the coefficients inside the argument of the cosine or sine or exponential, complex exponential, and they go from, and they add on and up and up and up. We haven't really talked about how you calculate the coefficient that goes out front, in front of the sine or the cosine or the exponential. That's what we're going to talk about now. That involves something called Fourier's trick, or that I call Fourier's trick, that my teachers called Fourier's trick. It's a nice way to think about it. And it helps you see how the Fourier series really works. There's another thing called the Fourier Transform, which is not integers increasing, but it's actually a continuous set of values inside that argument. We're going to talk a little bit about that, but we'll get to it after we deal with the Fourier series first. Okay, so the first thing you want to think about when you're thinking about Fourier series is you want to think about things on the interval from minus pi to pi. That's the bounds of our evaluation period. And so going from minus pi to pi, we can think of the average of things. So we talked last time in the integration little short lecture about the average being the integral of something divided by the integral of just the length element. So the integral of the length element from minus pi to pi is just 2 pi. So the integral of anything else is the integral of that divided by 2 pi. Okay, so what's the integral of something simple? The number 1. Well, the number 1 integrated from minus pi to pi is just 2 pi. 2 pi over 2 pi is 1. So not surprisingly, the average value of the number 1 over the interval from minus pi to pi is also 1. But what about cosine of nx or sine of nx? Well, we could do this because we know that the derivative of sine is cosine, so the integral would be of cosine nx would be 1 over n sine nx, and then we can evaluate it at pi, we can evaluate it at minus pi, and it turns out that it's always going to cancel out to be 0, because it doesn't matter what value n it is, it's going to be the same at both intervals. So it'll be 1 minus itself, because minus pi to pi, everything is periodic. All of these sines and cosines are all periodic on the minus pi to pi. So all of them are going to be canceling out on the endpoints. The same is true if we do start with the integral of sine and then we calculate the cosine. So then its integral would be 1 over minus 1 over n cosine nx. But it also is the same in pi and minus pi. And here's a quick little sketch of what I mean for the ones that just would have an nx. So if we go from minus pi to pi, we get the same value on both ends in the sinusoid and in the cosine. If we had a bigger n, not equal to 1, we get more wiggles, but the same would be true on both ends, and it would still end up being 0. So it's 0 in both cases. Okay. What about this funny beast? Cosine nx squared plus sine nx squared. Well, cosine squared plus sine squared is equal to 1. That is just the Pythagorean theorem for a right triangle with a unit hypotenuse. Okay, so if we have a unit hypotenuse, then we get 1. So the average value of 1 is still 1. That's just this one from before. That's cool. Okay, well, what if we split it into 2 parts, the cosine nx squared and the sine x squared in both parts? Well, we can go through and we can work out the integrals, or we could just notice that actually the only difference between cosine and sine is that they're shifted by a little bit. And that shift doesn't really matter if you go all the way from minus pi to pi, because that shift is just a little different. So you always get the same amount, seeing these, if you shift it over by 1, you get the other one on that same interval. So in fact, by symmetry, this one and this one have to have the same average value over that interval. So they're both 1/2. Absolutely. That's the quick way to do it, but unless something funny happens. Well, if n equals 0, then the cosine of 0 is just 1, and so this is back to being 1. So this is equal to 1/2 unless n equals 0, and this is 1/2 unless n equals 0, because sine when n equals of 0 is 0, so it would be 0 even if it was that. And then the last and the most subtle one of these is e to the I mx, e to the I nx. And this is the basis of the Fourier series in the complex space. And when you set it out as an average, you get e to the I mx, e to the I nx. And if you think about this as being, each of these as being like a cosine of mx, sine of nx, plus I sine of nx, cosine of nx, plus I sine of nx, and then you multiply them out, and you're going to see that it's going to become like kind of a zoo of these crazy things. But it's actually simpler to think about. What if m equals n equals 0? That's one interesting case. Then if this is 0, then this becomes 1, this becomes 1, and now we just have an integral of 1. That's the first case. What if m is not equal to n? Then we can add these together and we get e to the I m plus nx. And I don't know what m plus n is, but I can tell you that it's going to be equal to cosine of m plus nx plus I sine of m plus nx. And since the cosine of nx and the sine of nx are going to be 0 on both, and m and n are also integers, then this is going to be 0 for all of those, because it's always going to be a real part plus an imaginary part that are coming from the previous ones. Okay, so what's the interesting one? The interesting one is when m equals minus nx. If m equals minus n, then these two cancel, and we get a 1 in there, and we get a 1 back out. So it turns out that these are the only cases you need to worry about. If m equals n, if m is not equal to n, or if m is equal to minus n. I just realized there's one more case. What if m was equal to n? Then this would just be another sines and cosines. So that's no different from the m not equal to n case, or m not equal to minus n case. It's the m equals minus n case that's the important one that you have to single out, that equals 1. So that's the game. These are the averages of these functions. Okay, so what do we do if we want to find the Fourier transform of a series? And let's give ourselves something pretty simple. Here's a function which has a sinusoidal part and a cosine part. The sinusoidal part has no inner coefficient and no outer coefficient. This one has 2's in both locations. How do we do it? So what we're assuming is that we have this function and we can evaluate it anywhere we want. We don't know what it's made of, but we're actually going to show that we can find out what it's made of. Okay, so let's integrate f of x times sine of x. What's the average value? Well, when I multiply by sine of x, I get, this is the average value. I know this, but I don't actually know. If I was doing this and didn't know what the function was, I would just have to calculate this integral. I could just multiply it together and calculate it. But seeing what the function is, I see that I get a sine squared x plus 2 cosine 2x sine x. Well, which is which? This one is 0. This one is 1/2. 1/2. Okay. What about if I do it with cosine f of x times cosine of x? I will get 0 here and 0 here. What if I do it with f of x sine 2x? 0 here, 0 here. We're starting to see a pattern. What if I do it times f of x cosine 2x? I would get 0 here, 2, 1/2 cosine squared, so I will get 1 here. So you can see that if I was thinking of f of x as equal to a 0 sine of 0x, that's 0, plus a1 sine of x, plus a2 sine of 2x, plus ... plus b0 cosine of 0x, sorry, but cosine is just 1, so we have a constant, plus b0 b1 cosine of x plus b2 cosine 2x plus dot, dot. You can see that all I need to do to find a1 is to multiply the function by its partner, sine of x, and then evaluate it. In this case, I get 1/2. So a1 should actually, this should actually be 1/2 of a1, which in fact it is. What about sine 2x? Well, I don't have any sine 2x, but if I had it, I would have had 1/2 of a2, 1/2 of a3, 1/2 of a4, so on. What about the next part? The cosine part, well, I don't need a 1/2 for b0. That would be just the integral of the function itself. In this particular case, the function doesn't have any constant part, so its integral is 0 from minus pi to pi. But what about this b1 cosine x? That's also 0. b2 cosine 2x, that is that, but that's 1/2 b2. So this implies that b2 should be equal to 2, a1 should be equal to 1, and we have reconstructed our series. Now it turns out that there's a rather more complicated part of this whole process, which is called a completeness theorem, which tells you that these, in fact, are all the functions you need to express any function. These sines and cosines are complete in the space of minus pi to pi for integer sines and cosines. That's totally not obvious at all, but this is the machinery by which you determine those coefficients, and then the completeness tells you as long as you have a function that's you can evaluate these averages on, you can find it. And it's interesting that it even works when the function isn't continuous. If it has jumps in it, at least a finite number of jumps, you can still calculate these averages just by going up to the jump and then doing another integral from the other side. And in fact, the Fourier series still converges to those functions, including the jumps, except at the jumps, it'll go to the midpoint halfway between the upper and lower part. So Fourier series are really a pretty fascinating thing to use from minus pi to pi. So the next little part of the story is to think about what happens if we weren't thinking about the interval from minus pi to pi. What does that really mean? All right, so we've been talking about these integers, n times x, n times x, and we might sum from 0 up to infinity, and that would give us any function, as we said, from minus pi to pi. What if we made the interval bigger than minus pi to pi? Then effectively we would just be getting bigger numbers in here, but we'd also have to worry a little bit about whether they were actually periodic on that interval. Okay, so we've been thinking about taking an infinite Fourier series, which corresponds to the integral of the function times the sine of whatever it is, and that gave us this relationship between the sines and cosines, and every time you multiply by a mismatch sign, you would get nothing. That's something called orthogonality. If you multiply by the sign that is in the function, then you get a non-zero. If you multiply by a sine or cosine that's not in the function, you get a 0. That is the trick for how we find the coefficients. But actually, if we didn't have an infinite number of measurements, we wouldn't be able to fit an infinite number of series. There just aren't enough. In some sense, this is actually a linear relationship. It's our favorite thing. So we've got linear coefficients that we're looking for in terms of linear evaluations. This is an integral, it's a linear thing, of the cosines and sines. So imagine if we chunked up this integral into just a sum over discrete sampling intervals within. That's actually something called the discrete Fourier series, or the discrete Fourier transform. And in that case, you do the same procedure, and this is laid out in the notes, but you have an upper limit for the frequencies that you go to, and then you have only a fixed values of x that you evaluate the sines and cosines at. And then you use that with the same orthogonality principle, except now the orthogonality is a discrete orthogonality to find all the ANs and BNs. So here's the fun part. the finer you sample in X, the closer together your sampling intervals, the bigger you can take your sine and cosine order. So we can have higher and higher sines, but only if we have more and more samples in X. With the ultimate limit being that if we actually go all the way to the integral, we could go all the way to an infinite number of f of x's. All of an infinite order of f of x terms. Okay, that's cool. What about if we flip that over the other way and we say, all right, I've got an infinite numbers of n's and n's as I go up. What if I am trying to think about how precise I could be about these coefficients out front? Well, actually, because this has the symmetry where you're multiplying by one by the other, you can flip it on its head and you can go backwards. So from all the locations in x of a function of x, turning it into a function of coefficients with specified functions, I can instead think of these coefficients as being the thing that it's a function of, and then go backwards to find it as a function of x. That's the notion of the Fourier transform, where we are looking for coefficients that allow us for different values of n to go backwards. So I can think of this either as a function of n or as a function of x and go one way or the other back and forth. So if it's a function of n, then I have the coefficients which are dependent on n. And if it's a function of x, then I have it being the function of x. Now, if we go all the way so that the n's become very, very close together, then we might actually think of it as a continuous thing where we have a function of x and a function of n. Let me write that out. So writing that out, let's do the complex exponential form, which is the cleanest of that. If we think of a function of x, there's a normalization factor, which now has a square root of 2 pi for reasons that aren't terribly clear, but they are if you work out what I'm going to say. So I can go from a function that's of x to a different function that's a function of k, where k is playing the same role as the n's did up here, except now it's a continuous variable. And so k times x, e to the I kx, that looks an awful lot like multiplying by the e to the I kx to get our Fourier trick. So f of x can be generated from a g of k, but g of k can be generated from an f of x. There's a symmetry there. The only difference is the sign on the e to the I kx. These two have the same coefficient out front, which is the nice way to write it. And if you go through and do this, you will do this loop, you will actually see that this works. Well, other things have changed though. Remember how we said that you had to have finer and finer sampling to go higher and higher in n up here, in spacing in x. Here we have just as fine as we want because both x and, this is an integral in k, this is an integral in x. We have here, we're summing over n, but x is continuous to allow us to go to infinity. Here, we're integrating over k, or we're integrating over x, both. And that means that we have to get finer and finer in both k and x, but we want to go to higher and higher values in both k and x, so we can't stay constrained to just the minus pi to pi anymore. So essentially the fact that k has become continuous rather than discrete means that we need to expand our integral when we're doing this kind of an expansion to be minus infinity to plus infinity rather than minus pi to pi, and vice versa going the other way. In order to get enough resolution to have very, very high k's, we need to have x be continuous. So k is continuous, x is continuous, both of them have to go from minus infinity to infinity in order to have this full transform form. If we had an odd function, we can do the same thing with our basis of odd sinusoid functions. And that looks a little bit like this. So we can get, so an x function can be composed of lots of sines with a function of k to give the equivalent of the amplitude functions up here, but it's a continuous function of k. We're integrating over all minus infinity to plus infinity. And then there's an inverse transformation where we can find the gs of k, which is gs of k, which looks an awful lot like this one, because we know that the sine times the sine, the only way that that works out is when they actually equal each other, at which point they sum up. There's a cosine transform, which looks very similar, except the cosine's in the place of sines. So if you wanted to capture a whole function that had both odd and even elements, you could do both a sine transform to get the odd part and a cosine transform to get the even part. That's it. So we have the Fourier series, the discrete Fourier series, which is chunky in x, has a limit on k. We have the infinite Fourier series, which is continuous in x, still chunky in k or n, and there's only integer values. And then we have the Fourier Transform, which is continuous in both k and x. And then you have to expand the limits out to infinity in both directions in order to get when you go far, far, far out in the k space, it allows you to get very, very fine in the x space. And when you go far, far, far out in the x space, it allows you to get very, very fine in the k space. There's a symmetry between those two. So if you want to have really high resolution in a discrete Fourier transform, if you want to have really high resolution in k's or in n's, you have to have a really long record. If you want to have if you want to have a very high k at the top point, you need to sample that record very finely. And so going to the continuous case does both of those. We sample infinitely finely in a continuous, and we have an infinitely long record in order to have the other one be continuous and also lengthy.